basic question is, does life exist beyond Earth? Scientists who are called astrobiologists are trying to find that out right now. Most astrobiologists are trying to figure out if there's microbial life on Mars or in the ocean under the frozen surface of Jupiter's moon Europa, or in the liquid hydrocarbon lakes that we've found on Saturn's moon Titan. But one group of astrobiologists works on SETI. SETI is the search for extraterrestrial intelligence. And SETI researchers are trying to detect some evidence that intelligent creatures elsewhere have used technology to build a transmitter of some sort. But how likely is it that they will manage to find a signal? There are certainly no guarantees when it comes to SETI, but something called the Drake equation, named after Frank Drake, can help us organize our thinking about what might be required for successful detection. If you've dealt with equations before, then you probably expect that there will be a solution to the equation, a right answer. The Drake equation, however, is different because there are so many unknowns. It has no right answer. As we learn more about our universe and our place within it, some of the unknowns get better known, and we can estimate an answer a bit better. But there won't be a definite answer to the Drake equation until SETI succeeds, or something else proves that Earthlings are the only intelligent species in our portion of the cosmos. In the meantime, it is really useful to consider the unknowns. The Drake equation attempts to estimate the number of technological civilizations in the Milky Way galaxy, we call that N, with whom we could make contact. And it's usually written as N equals R star multiplied by F sub P multiplied by N sub E multiplied by F sub L multiplied by F sub I multiplied by F sub C, and lastly multiplied by capital L. All those factors multiplied together help to estimate the number of technological civilizations that we might be able to detect right now. Our star is the rate at which stars have been born in the Milky Way galaxy over the last few billion years. So it's a number that is stars per year. Our galaxy is 10 billion years old, and early in its history, stars formed at a different rate. All of the F factors are fractions. Each one must be less than or equal to 1. F sub P is the fraction of stars that have planets. N sub E is the average number of habitable planets in any planetary system. F sub L is the fraction of planets on which life actually begins, and F sub I is the fraction of all those life forms that develop intelligence. F sub C is the fraction of intelligent life that develops a civilization that decides to use some sort of transmitting technology. And finally, L, the longevity factor. On average, how many years do those transmitters continue to operate? Astronomers are now almost able to tell us what the product of the first 3 terms is. We're now finding exoplanets almost everywhere. The fractions dealing with life and intelligence and technological civilizations are ones that many, many experts ponder, but nobody knows for sure. So far, we only know of one place in the universe where life exists, and that's right here on Earth. In the next couple of decades, as we explore Mars and Europa and Titan, the discovery of any kind of life there will mean that life will be abundant in the Milky Way. Because if life originated twice within this one solar system, it means it was easy, and given similar conditions elsewhere, life will happen. So the number 2 is a very important number here. Scientists, including SETI researchers, often tend to make very crude estimates and acknowledge that there are very large uncertainties in these estimates in order to make progress. We think we know that R star and N sub E are both numbers that are closer to 10 than, say, to 1. And all the F factors are less than 1. Some of them may be much less than 1. But of all these unknowns, the biggest unknown is L. So perhaps the most useful version of the Drake equation is simply to say that N is approximately equal to L. The information in this equation is very clear. Unless L is large, N will be small. But, you can also turn that around. If SETI succeeds in detecting a signal in the near future, after examining only a small portion of the stars in the Milky Way, then we learn that L, on average, must be large. Otherwise, we couldn't have succeeded so easily. A physicist named Philip Morrison summarized this by saying that SETI is the archaeology of the future. By this he meant that because the speed of light is finite, any signals detected from distant technologies will be telling us about their past by the time they reach us. But because L must be large for a successful detection, we also learn about our future, particularly that we can have a long future. We've developed technologies that can send signals into space and humans to the moon. But we've also developed technologies that can destroy the environment, that can wage war with weapons and biological terrorism. In the future, will our technology help stabilize our planet and our population, leading to a very long lifetime for us? Or will we destroy our world and its inhabitants after only a brief appearance on the cosmic stage? I encourage you to consider the unknowns in this equation. Why don't you make your own estimates for these unknowns and see what you come up with for N? Compare that with the estimates made by Frank Drake, Carl Sagan, other scientists, or your neighbors. Remember, there's no right answer, not yet.